So in this video, we are going to try and solve a couple of IIT JEE level problems. The first problem is from the topic of hydrostatics, and the problem goes like this. It has been given that we have a U-shaped tube and the length of that tube is L, and a liquid fills that tube but only up to this level. It only uh, occupies the length L of the U-shaped tube, and it doesn't go up to any height along the arms of the tube. So this is the level up to which the liquid is filled. The density of the liquid is rho. Whatever that liquid is, its density is rho. Now what is said? It is said that this entire U-shaped tube is rotated about this arm, about an axis passing through this arm at an angular velocity of omega. When that is done, when this tube is rotated like this with an angular velocity omega about this axis, so what is happening here is that this is the axis and the U-shaped tube, the entire tube, is rotating about that axis. So this arm remains in place while the rest of the tube rotates about that arm, or an axis passing through that arm. So what happens when it's done, when that is done, is, say we consider an element of liquid, an infinitesimally small element of liquid here. Because this element is at a certain distance from the axis, and because the whole U tube is rotating about that axis, this element also, it rotates around a circle like so, and therefore a centrifugal force acts on that element, and what it does is it pushes that element to that side. So what is happening is the liquid in this portion is being pushed to that side. So it has been said, it has been given that liquid is pushed up to a distance y from this arm, and when that happens, because liquid is incompressible, the liquid in this arm will also rise up to the same height y. So the liquid originally was filled up to the entire length, but when the U tube is rotated about this axis, every elementary differential element of liquid in the arm experiences a centrifugal force to the right, to the positive x-axis, and therefore there's a certain motion of liquid which pushes the liquid up to a distance y from this arm, and because liquid is incompressible, the liquid in this arm rises up to the same height y. So this much length is actually L minus y. The column of liquid that we have will retain the same length y. So the question that is asked, oh, I forgot to say one thing. It has been given in the question that this arm remains open while this arm is closed, so that atmospheric pressure can act through this arm, but no atmospheric pressure acts through this arm. There will be pressure in this arm to balance the net centrifugal force. There will be a certain force will act from this arm, but whatever that pressure will be, it won't be atmospheric pressure. So it has been given in the question that this much length is y, and we know that this much length will also be y because liquid cannot be compressed, and they are asking us to find what the pressure in this arm is. Let me call that pressure P dashed. So if we concentrate on this differential element, infinitesimally small differential element, we can say that because this element also rotates in a circle, it experiences a certain centrifugal force. Let us first find out what that centrifugal force is. So that centrifugal force will be the formula for centrifugal force. We know the formula for centrifugal force is mr omega squared. So the centrifugal force on this element will be dm r being the radius of the circle along which the infinitesimally small element rotates, times omega squared, omega being the angular velocity. Now what is dm? dm is the small mass of the differential element of liquid, and mass is volume times density. So density is just rho. What is the volume? Volume is cross-sectional area times length. So let me say that, I wish I had a different color. Say this much length is x, that is the distance of the differential element from the axis of rotation is x, and a small increment along x can be called dx, and dx therefore becomes the length of the elementary column. So the volume is cross-sectional area times length. We are finding the volume of this element. Its cross-sectional area is capital A, and its length, say, is dx. Dx being a small increment along x times omega squared. If I draw the small element of liquid separately here, we can say, or we know, that centrifugal force dF acts from that side. But once the entire column of liquid has attained this particular shape, that is, this end is at a distance y from the axis of rotation, and this end has risen by a height y, the element is now in equilibrium. It is no longer moving. There is nothing else is happening here. All the forces are balanced now. Before this equilibrium condition had been reached, there was a centrifugal force, and the pressure here wasn't enough to contain that centrifugal force, and therefore the liquid level rose. But at this particular moment, everything is in equilibrium. So we can say that if pressure from this end acting on the small element is P, the pressure from this end will obviously be slightly greater, P plus dP. The excess pressure dP, the unbalanced pressure dP, will balance the centrifugal force. So we can say that dP times cross-sectional area A will have to be equal to dF, because we are talking about the equilibrium condition. So in place of dF, we can write dP times A, and we can cancel the A's out. Okay, I've missed the R in the second line, so let me put it back. But what is R? R is the radius of the circular path of this element, which is actually x. If I can try to draw the circular path, if this is the circular path of this element, the radius is x. So in place of R, we can substitute x. So we can say that dP is rho x omega squared dx. So we have found the excess pressure acting on this element. If we add up all the excess pressures acting on all the elementary differential liquid lengths along this line, we can find out the entire excess pressure acting along this line. So if we integrate both sides, I'll just take the constants out of the integration sign. So rho omega squared is constant. The pressure acting from this side is just atmospheric pressure. PA, the pressure here, let me call it just P, and X starts from Y and goes up to L. So X, which is this length, actually we start from here, the place from which the liquid column starts, it's Y, and we go up to L because we have to find the pressure here. So we start from this point, at which point the pressure is just the atmospheric pressure, because this arm of the U-tube hasn't been closed, it is open, so atmospheric pressure acts from this side. So we have a PA here, and X also starts from here. At this point X is just Y. We go up to here, at which point X becomes L, and we assume that the pressure here is P. So after integration of dP is just P, and if we substitute the limits, we get P minus PA. We get a rho omega squared here. Integration of x dx is just x squared over 2, and if I substitute the limits directly, I get L squared minus Y squared all over 2. So we can easily find what the pressure here is. So the pressure there becomes rho omega squared over 2 L squared minus Y squared plus the atmospheric pressure PA. But note, we have been asked to find the not the atmospheric pressure, but the pressure in this column. So if the pressure in this column is P primed or P dashed, we can say that P dash we can actually say that P minus P dash, the difference of pressure between this point and this point, the pressure here being more than the pressure here, is just rho gy. So we can easily find what P dashed is. P dashed is P minus rho gy. So P dash becomes, we just substitute the expression for P here. So that's rho omega squared over 2 L squared minus Y squared plus PA minus rho gy. So that's our final answer. So that completes the first problem.